Hello everyone. Today I'm going to be doing a presentation on steady states of mountain belts, and the core concept of it would be dynamic equilibrium. So let's start. Basic concept of a dynamic equilibrium is when when more than one force actively acting in a different directions or in different ways counteracting each other, and when all forces are balanced, we come to some sort of a stable point. However, it does not mean that nothing is going on. It just forces actively counteracting each other and found some stable point, which we call dynamic equilibrium. As an illustration, I'm showing here thing that can many people can relate is the bathtub. As we can see, we can have water running, and we can have water leaving the bathtub at a certain rate. And if the influx and outflux match each other, we would have water at a certain level. And as long as they are matched, the level will be maintained. If suddenly we have influx or outflux change, then the water level will rise or drop as a result. So in that case, we wouldn't be able to say that the system is in dynamic equilibrium. However, at the point when they are matched, we can state that the system is at dynamic equilibrium. As we understood this principle, let us move on to the next slide. And in geomorphology, we can illustrate with a simple um, drawing that I made what is dynamic equilibrium when it pertains to mountain belts. We have uplift, tectonic forces of crustal plates as they move around and they bump into each other, they begin to buckle and rise. As they do so, however, we increase the rates of erosion. At some point, those two forces of uplift and erosion would be matched, and the mountains would be at a steady state. They would be in dynamic equilibrium. Doesn't mean that erosion is not happening or uplift is not happening. It means that at that point in time, uh, that the balance is reached, and as long as both forces are about the same, the mountain belt will remain to be at that height, although the active process on both ends are still going on. And this is a very useful basic concept to understand that we will see further on. Let's move on to the next slide now. Here, the paper that was analyzed proposed four types of dynamic equilibrium. First, we have flux in and flux out, and that means that as two plates collide and one would, let's say, subduct and push the other one up, it begin to increase. So this is our and it would uplift a certain area. This is our flux in. The flux out is the amount of material that is being eroded. It doesn't refer to the height per se, it just refers to the amount of material that's being uplifted and amount of the material that's being eroded away. This is the first idea of dynamic equilibrium when it pertains to the volume of the material as it being accreted and as it being eroded. And the second, we have a topographical steady state, and that is what in a way was mentioned earlier. It might not per se refer to the volume, but to the general topography of a mountain belt, where its general shape and height and width remains more or less the same throughout time, and this is what we might call a topographic steady state of a dynamic equilibrium. Um, Third one is what we can call thermal steady state. In a thermal steady state, as we reach some dynamic equilibrium, we know that with depth our temperature increases. And if other things are true, that we reach equilibrium point, there will be a point where the increase in temperature with depth would be maintained throughout time. So even though we have still uplift and still erosion, if we were to be able to drill and place thermal sensors in a certain place and be able to maintain them for a long enough period of time, we would see that with depth the temperature is maintained. And this is an important concept for the next one, and that is exhumational steady state. And that is in a way tied to all the previous ones, that we have different strata that have been uplifted and eroded, and at the rate at which it happens, this is called exhumation, can also reach this steady state. And as I make a very basic illustration showing different strata there, we see that even though the strata are different, but at the rate at which they are uplifted is maintained. This is called exhumational steady state. Now let's move on to the next slide so we can in more of a detail discuss each one of them. This is a basic it's a basic diagram of what flux steady state would be. We have FA is our flux in, as one plate collides with another and buckles and begins to uplift. So this is our FA. And then, as it begins to uplift, we have increased erosion on both sides of a mountain range, which we marked here as FE. And if the system is in flux steady state, FA would be equal to all of the FE. That is going to be a flux steady state. Pretty much just a more visual explanation, more a nice diagram and a pretty simple equation if we can, of course, correctly identify what is FA and FE. So that is our first part of a steady state, flux steady state. Now let's move on to the next one. This is topographical steady state. Topographical steady states, as we can see here in this evolution of a mountain range, how it evolves when we have inception of an uplift and it comes up, that you might create a certain shape, and that shape might be due to various factors. Some of them, one of it is just the direction of the plates moving that creates a skew in a range. Another one is most likely the effect of our orographic uplift. What we have is, because it usually happens on the margins of oceanic and continental plate, oceanic plate would be subducted under the continental plate, and we would have on one side of a mountain range would have ocean, on the other would have continent, and ocean being producing humid air masses. As it collides with the mountain range, it begins to be orographically uplifted, would then begin to precipitate, causing more precipitation on one side of a mountain range and not the other. And difference in precipitation would, of course, create different rates of erosion, where and increased erosion on one side, in addition to more vegetation, would create different shape of a mountain range and a difference in terrain that over time, if all forces are maintained in a dynamic equilibrium, would be the shape of a mountain range would be maintained. This, however, doesn't mean that if we zoom in and look at the individual slope of an individual hill or peak in the mountain range, that it would be. No, it wouldn't. It is more of a statistical zoom out approach where we look at a larger picture, because on a micro level, of course, there will be drastic changes, but on a macro level, the shape of a mountain range would be maintained. And now let's us move on to the next slide. Here we talk about thermal steady state. As in a first slide, we know with the depth temperature increases, and that temperature increase, if we have steady state and things in dynamic equilibrium, we can conclude that the increase in temperature would be maintained over time. Here we see different layers as they're marked T1, T2, T3, and T4. Just for illustration purposes, we can say that through time, their depth and their magnitude would be maintained. And that is very important for the next part, because as we draw this isotherms and show that the temperature gradient increase, and if we can prove that they are maintained the same, then we can then use it to calculate exhumation rate and see if there is in fact exhumational steady state. But for that we have to go to the next slide to see how we can accomplish that. Here we have thermochronometers. Thermochronometers are unstable radioactive isotopes that are set at certain temperatures. What it means is, if the temperature is too high, minerals, as we know, if hopefully people watching it can tell, that radioisotopes are unstable elements that decay mother to daughter. There could be multiple chain of them, but as we can see here, for different elements at different temperatures, things can sort of move in and out of a mineral. If we can imagine that there is a certain strata composed of a that has some lithology at a temperature that's above a certain threshold for individual isotope, the mother-daughter elements can move in and out. They can migrate. It does not necessarily mean that the rock is molten. It just means that there's some mobility still. The window to move the elements in and out is open, and therefore the clock isn't started. However, at certain threshold temperature, the structure of whatever element is set that individual elements cannot move in and out, and as our half-life of each element is not affected by temperature, pressure, or any other force that we're aware of, and the proportion between mother and daughter maintained and they're locked in, sort of the system becomes a closed system, then we in a way start a stopwatch, and we can then see we can see at which when a rock came to the surface and we count the proportion between mother and daughter element, we can then tell, knowing the half-life of this element, when the stopwatch was started and how much time had passed. And if we see that in a certain mountain range that rate is equal, we can then conclude what would be discussed in the next one, and that is exhumational steady state. As we mentioned before, we can calculate the flux. We can see that topographical steady state maintained. We can see that the thermal steady state maintained. But then knowing that, we can also see that a different point of a mountain range, we might have a different exhumation rates by checking this thermochronometers and seeing that for different rocks we might find different thermochronometers, but if we date them and they come out at the same date, it means that at whatever depth the clock was set, from that depth to the surface past a time that the rock was dated to. And this is how we can calculate the exhumational steady state. Again, pretty simple concept if we put things together and we follow through. So let us move on to the next one. How can we apply this knowledge? One of the idea is with the change in temperature and climate variation that will be affected by the change in global temperature, erosion rates would be different. If the erosion rates are different, it would of course affect our flux out, and there's a attempt to use the thermochronometers and assumption of a exhumational steady state. If we can determine what is the rate of exhumation now versus if we try to model for different different climate, as for instance we have a proposed increase in temperature of 1.5, 2.5, 3 degrees or so, we can see how the precipitation at those temperatures would affect the exhumation rate. And this is what this paper attempted to do, although the results were inconclusive. This is still a very new information, and perhaps more modeling is required. This was just one of the examples that I was able to find of a paper that is about 10 years old. So these are the resources I used in this short presentation. Feel free to try them on, and I hope you like the information. Thank you so much.